So if I have a vector space V and some vector within V, and B is a set of vectors, and that's a basis for the vector space, and that vector V is equal to some linear combination of the basis vectors, C1 times B1 plus C2 times B2 all the way to Cn times Bn, then the representation of V with respect to B, the basis, is equal to the vector containing the coefficients in order that I multiply the basis vectors by in the linear combination of them in order to equal the vector V. It was equal to C1 times B1 plus C2 times B2 all the way to Cn times Bn, and so the representation of B with respect to B is C1, C2, C3, C4 all the way to Cn in a vector. So here's an example. Remember that basis B earlier that we actually verified was in fact a basis? We checked its span, we checked if it was linearly independent or not. It was the set of the vectors 2, 0, and -1, -1. When we checked its span, we were finding what scalars C1 and C2 make the linear combination C1 times B1 plus C2 times B2 equal to XY, where XY is just any vector in R2. And we found that these two scalars did indeed exist, and that C1 was 1/2 x minus 1/2 y, and that C2 was -y. So let's say I wanted to find the representation of the vector 3, 4 with respect to this basis. Well, that would equal the vector of scalars that I multiply the basis vectors in B by in order to create the vector 3, 4 out of a linear combination of them. So those scalars are C1 and C2, and we have the formulas for them right here. We find them when we check for span. And so when you have to find the representation of a vector, you really just do the span calculation and put C1 and C2, or C1, C2, and C3, however many scalars you're looking for, into a vector. That representation is going to be 1/2 of x, which is 3, minus 1/2 of y, which is 4. And that second component, C2, is going to be -y, -1/2, -4. Or, in case this wasn't obvious to you already, how about the fact that the representation of any vector with respect to its standard basis is just equal to itself as it was written before? This is because we write vectors in the standard basis by default, which you may have realized already, and so to represent them with respect to that basis would just be to give the same vector. Here's an interesting space that we can look at. This is the space of quadratic polynomials, P2. And so it's the space of all polynomials of the form a plus bx plus cx squared, where a, b, and c are any real numbers, b and c are just coefficients, and a is the constant. I think a good contender for a natural basis equivalent for P2 would be the basis 1x x squared. This is basically the same thing as the standard basis in R3 because 1x and x squared represent actually traveling one unit along each of the three directions in P2. Now these aren't the x, y, and z directions, these are the constant, linear, and quadratic directions, or the 1x and x squared directions. And so let's say we have some other basis d, and d is equal to 1 minus x squared, 1 minus 2x x squared. And I want to represent the polynomial -2 plus 2x minus x squared with respect to the basis d. Well, I could do the whole span calculation, but actually there's kind of an easier way to go through this. Notice that the polynomial we're trying to represent has a 2x in the middle. It has a linear component. Well, which of the three polynomials in d could we get a linear component from? The first polynomial has 1 minus x squared, but there's no linear part. And the last one also has no linear part. It's just x squared. The middle one is actually the only one that we could get this 2x from. Specifically, it looks like if we took -1 of this portion in the middle, we would have -1 plus 2x, and therefore we would have 2x in the middle. So it looks like we're definitely going to need to take at least -1 of this middle polynomial in the set D. So now we have -1 plus 2x. I know that we need a -2 out front, but right now we have a -1 out front. So other than this middle polynomial, where else could we get a constant portion to our end result, -2 plus 2x minus x squared? Well, the last one doesn't have a constant portion, but the first part does. In 1 minus x squared, 1 is a constant. So in order to turn -1 plus 2x into -2 plus 2x minus x squared, the next step that we're going to have to take is subtracting 1 from -1. It looks like we're also going to have to take -1 of the first polynomial in D. We subtract 1, but we also add x squared. We get -2 plus 2x plus x squared. Well, this isn't quite what we need because we actually need a minus x squared at the end. So it looks like we're going to have to add a certain amount of the remaining member of D in order to subtract 2x squared from x squared. And in that case, we're going to need to subtract 2 of the final element of D. And so the representation of -2 plus 2x minus x squared with respect to basis D is -1, -1, -2. This method doesn't just work for polynomial spaces, it works for any kind of space. I wouldn't recommend it for super complicated problems, but if you have a problem like this where you understand that a certain component of your final result can only be sourced from one of the elements of the basis, in this case 2x could only be sourced from the second element in D, then you can use this method. Now we're going to talk about dimension. So if I told you that R2 was 2-dimensional, or that R3 was 3-dimensional, you would probably know what I mean, because we can visualize R2 and R3. We imagine that R2 gives us 2 degrees of freedom in our motion, R3 gives us 3 degrees of freedom in our motion, and if I told you that R4 was 4-dimensional, you would probably take my word for it because it seems like it follows this pattern. In general, when I have a vector space V and it has a basis B, the dimension of that vector space, okay, so dimension applies to the vector space, is the size or the number of elements in the basis. Now you might be thinking, well, can't I have multiple bases for a vector space? Yes, but since a basis is a minimum spanning set, all bases have to have the same minimum number of vectors in them required to span that set. So there are multiple bases that we could choose for R2, R3, or in general a vector space V, but they all have to have the same number of elements, and that number of elements for any basis for a vector space is the dimension of the vector space. To prove this, we're going to derive something called the exchange lemma. So a lemma is like a theorem, but it's just a bit smaller. So this lemma states that if I have a basis B, which consists of the vectors b1 to bn, and that's a basis for a vector space V, and then I have some vector V within that vector space, and that's equal to a linear combination of the basis vectors. Specifically, it's equal to C1 times the first basis vector B1 plus all the way to Cn times Bn, the last basis vector, and somewhere in the middle I have plus Ci times Bi, okay, so there's a Bi, that's some ith basis vector in the middle of this set, and when I take Ci times Bi, and that's a part of the linear combination, that scalar is not equal to 0, and that could be any Ci. Then, if I construct a new basis B prime, where I have all the same vectors as I did in B, except I replace Bi with V, then that is also a basis for V. So I'm exchanging V for Bi. So to start this proof, let's just notice that if B is a basis, then B is a set of linearly independent vectors. In which case, if I construct the linear relationship where I take some linear combination of all of these vectors and I set it equal to the 0 vector, then the only relationship that could hold would be the trivial one. That is, where all of the scalars d1 to dn are equal to 0. In the middle here, I have the vector bi, and in my new supposed basis, b prime, I replace that with the vector v. Well, the vector v is equal to this linear combination of all the vectors in B, so I can rewrite this linear relationship as follows. So d1 times b1 plus all the way to di times this linear combination of the vectors in the original basis B, which is equal to v, plus all the way to dn times bn, is equal to the 0 vector. So if I distribute this di to everything inside, you'll notice that bi is now multiplied by di times ci. That's the coefficient. That's the scalar. And then all the other basis vectors from B are multiplied by similar scalars too. For example, when I distribute di to C1 times B1, I get di times C1 B1. And then at the beginning, I have D1 times B1. And then I'm adding to that di times C1 plus B1. And so in total, this has the scalar D1 plus di ci times b1, and etc. All of the vectors have something like that, but the one that's actually important is the one that multiplies bi. The reason why is because one of the assumptions we made in the setup for this lemma was that ci was not equal to 0. However, this ends up being a linear combination in some way, right, with scalars like this or scalars like this of all the vectors in B. And B is a basis, and so it's linearly independent, so any linear relationship among those vectors that is equal to 0 must only be the trivial relationship. Therefore, all of these scalars have to equal 0. Therefore, di times ci has to equal 0. But if ci is not equal to 0, then the only way for di times ci to equal to 0 is if di equals 0. And if that's the case, then this whole term goes away, and I just get a linear combination of all the other vectors in B, which looks like this. And notice that this is a linear combination of vectors that make up a subset of a linearly independent set. So this set of vectors, b1 to bi minus 1, and then bi plus 1 to bn, is also a linearly independent set, and therefore the only linear relationship of this type that can exist among them is also the trivial relationship, so all the other d's equal 0, and so b prime is independent. I hope that this lemma does make a degree of intuitive sense, because if you think about it, B is a basis, which means that all these vectors are pointing in effectively unique directions in space. They contribute something unique in the way of span, And if I'm replacing one of them with another vector that can be represented as some linear combination of the vectors in the basis, some of those vectors in that linear combination might be multiplied by 0, so maybe v is equal to 0 of b1 plus 0 of b2 plus 3 of b3, etc. Not all of them are actually included in creating v. I know that at least v is equal to some non-zero amount of bi plus all the other vectors. And so if you think about it, v is still preserving some of what bi contributed in the way of direction. It preserves a non-zero amount of the direction that that vector pointed in. And so if I were to get rid of v, it's not like I would be able to express anything about going in that direction that bi initially pointed in with any of the other vectors, because they didn't have any of bi in them. So here's how we can use the exchange lemma to demonstrate that if I have two bases for a vector space v, then they have to be the same size. So I already know that both of these are vector spaces, but I only know the size of one. B has n elements, b1 to bn, and I'm not sure of the size of d, but I can construct a new basis, b prime, which is equal to b1 d1 to bn. What this means is exactly what we were doing with the exchange lemma. So d1 I can represent as some linear combination of the vectors in b, because the vectors in D, the vectors in B, the vectors in V, they're all members of this vector space. And since B is a basis for the vector space, it spans the whole thing, and so any vector in the vector space, including D1, can be represented as a linear combination of the vectors in B. So D1 is equal to some linear combination of the vectors in B. And within that linear combination, it's going to equal some non-zero amount of some vector Bi, which was right in the middle, just as we saw in the exchange lemma. And so I can exchange D1 from the basis D in place of bi in the original basis b, and construct a new basis which has all the same vectors from b, except that bi is replaced with d1. And I can just iterate this process over and over again, replacing each of the basis vectors in b with the vectors in d, as long as those vectors in d are equal to some non-zero amount as a part of the linear combination of whatever vector in b I'm replacing them with to construct a new basis, over and over again. And I will always be able to do that, and I eventually get a basis which is equal to a whole basis of these d vectors, and then there's one b vector in the middle. And I finally exchange the last d vector, wherever it is in this set, with that b vector, and I've constructed a new and final basis which is just d.